one.
Yes, so's mine. All right. Well, hello, everyone. Welcome to PyData Global. And so glad you can join us on our next, I guess this is our tutorial in the LLM track. Um, and our next person is Cainã. Are you able to share your slides there? Get that
Yeah,
pulled
let
up?
me share it right now.
Awesome.
Window. I'm going to change it later because I'm going to present the slide and after the code section directly.
Okay.
So
Perfect. So, right. So, as I said, so for folks, this is a tutorial. So this is an hour and a half long. And so I will let your wonderful host share with you how they'd like you to engage with this session. But as for this, I think we'll kick it off right now and let things go. Towards the end of the session, I think this is the last one in this track for today. So we don't have to quite kill it at time, but we can go a little bit over. But hopefully, we'll get a lot accomplished in the next hour and a half. So with that, I will hand it over to Cainã. Take it over. Take it away.
thank you so much, and thank you all for joining this section. Uh, so yeah, my name is Cainã. I'm a biologist, and I have worked in industries and academic research for the past like 10 years. Basically, currently I'm postdoc at UW University of Wisconsin, Madison, the US. And today I'm going to talk about the PyTorch workflow mastery. That's the title of the presentation, to introduce you a guide to track and optimize model performance. So basically, the goal is we're going to have a lot of hands-on in this project on this section. And I'm going to walk you through the base PyTorch workflow, how it looks like, how we train a model, and incrementally, you're going to increase a little bit some extra layers of complexity. For example, you're going to track our models using weight and biases, and then you're going to optimize our model using Optuna. And then finally, going to modularize our project using UV. That UV is a new Python project management tool. So I install UV. So that's what we're going to use here. Okay. It's kind of to support or replace poetry, conda, and everything. It's way faster. And I'm going to ask to use weights and biases to track the model performance. So let me log in here. And of course, I'm going to share the code with you. I don't have a link to presentation because I don't have enough slides, but I have a link for the GitHub repository that I'm going to share with you shortly. So for now, let me actually exclude this project because I'm going to start it over. And this here as well. So we're going to work with weight and biases, and you're also going to work, it's kind of similar to MLFlow. Not sure if you have heard of MLFlow, but there are tools to track the model performance. And you're going to use Optuna to optimize our model intelligently, okay? Because it uses Bayesian search to search in a space of hyperparameters to find the best hyperparameters for a model in a smart way. So you don't need to spend that much time to find good hyperparameters for our model. So that said, I think I can share the code directly with you, and then you're going to have the hands-on project. So me share it again, VS Code. Mhm. Let me clean it here. Let me increase it here. Is the screen visible for you? Okay, can you like read it? Let me provide some extra zoom here. So, okay, so basically that's our folder structure. Let me just, sorry about that. I forgot to ignore it. So basically that's our folder structure. And I'm going to walk you through the basic ways we can use uh, PyTorch for building. In this case, we're going to use a dataset called CFAR10 dataset. I think I can share with you. Fortunately, I cannot share the region of my screen. I can only share a specific window. Right. Because there we go. Sorry, let me change it here quickly. We can't hide this here. So we're going to work with a very simple data set, okay, for this task, and have made it on purpose because the goal of the presentation is to provide familiarity with the PyTorch workflow rather than complexities of handling data sets. But for real life data sets, you're probably going to have extra steps about pre-processing the data and possibly post-processing the data as well. So here we have like 10 different classes. They are very small pictures. You see here, zoom in, let me open a new image. So have a very small picture of 32 pixels by 32 pixels. I have like airplane, birds, horse, dog, cat, and so on. So definitely different pictures. And the goal is like to predict when we receive a new picture, we want to predict if this picture belongs to, I mean, is about a car, is about a bird, about a cat, and so on. But PyTorch is not only about computer vision. We can like classify images like these. You can classify, you can have like object detection to draw body boxes. You can like have segment detection. So to detect like the boundaries of the object, for example, detecting a human, you can detect the head, the arms, the legs, and so on. And can also work with large language models for text data, and can also work for audio data, for music data. So PyTorch is a deep learning framework, so it's suited to work with unstructured data, and can build amazing things with PyTorch, with Keras as well. So yeah, let's go straight to the code. I'm gonna okay, I'm going to push this link to the code because I haven't pushed the repository, so I can do it quickly here. But let me first walk you through, and then, but I'm going to, let me push this, place the link here of my GitHub repository. I'm going to push the code pretty soon to the repository, okay? As this talk ends. But okay, so basically that's how it's structured. So we're going to have 4 main notebooks. The first one I'm going to walk you through about, oh, I have made it wrong here. Optuna, that's the third one. Just change here. I have It's something wrong. Okay, so the first code we're going to walk through the basic PyTorch workflow is pretty basic. So perhaps you have already experienced PyTorch. It's not going to be news about it, but then we're going to implement weighting biases, and then we're going to link Optuna with weighting bias, and finally going to modularize, see how we can like change the structure of the code so I can have best machine learning operations practice. So I can deploy the model efficiently, you can share the code, you can make it sustainable for a long-term process. So how the code that are going to work is the notebooks is going to be in a folder called notebooks. And this the first part of the code is just to make sure the working directory is the root of the directory. So once you git a clone this Git repository, I'm going to provide the instructions, but in order to create the environment, let me remove the current environment so you can see it. In order to make it reproducible, we need to have like a specific Python version, a specific Python dependency one. And like I said, we're going to use UV to do it. So I have these main points of configuration of the project called pyproject.toml. And these here have some basic information about the name of the project, some description about it. We have all the dependencies listed here. We have an extra dependency, so I can like test, like provide a linting of the code and so on. And for my case, perhaps you can change it from your side, but for my case, I have a GPU in this particular version, so I'm going to use it locally. So I'm passing the index here to make sure I'm installing this specific version. After we are done with the notebooks, we're going to modularize the code. When I say modularization, like we're going to take every main logical piece of the notebook and start splitting it in functions, separate functions and classes. And we're going to create a package out of it, so we can install a package, we can like modify and see the modification in real time. Okay? And here's just some specifications about the linting process to make sure all the code has some standard specifications. And we can install everything after we install UV. This too, we can like enter the repository and type UV sync. Okay, so since it's cached already, I have done it before, it's pretty fast. But UV, you're going to see it's pretty fast, like 100 times faster than PEEP, for example. So yeah, Chris, in this moment, I need to push the code for the repository. I'm sorry about it. I was just worried about making everything work here. So I'm going to push it pretty soon. The repository is there. I just need to push it. Okay. Okay. So once you do this, it's like a magic. We're going to, everything is already, and you're going to see this folder here. It wasn't here before. I can ever remove once more the code repository. Oh, sorry, not the repository, the virtual environment. So you see, we don't have any kind of virtual environment. And when I do this, it's going to take all specifications of this file and it's going to install the dependency. It's going to use a specific Python version that is also mentioned here. So he's like equal greater than 3.12, and it's going to create a file like this, the Python version. It's going to make it very reproducible. So we can like activate the environment after that. If it depends of your operation system, but for Linux and Mac is like this, with source.env being activated. And here you go. Another thing that you can do later is like to install our package in an editable way. So you can like modify the code and once you save the script, you can use it directly. But let's do it later. Let's start from the basics. So how does PyTorch work? Uh, Here I'm going to show how to create, how to train a model, how to load the data. So basically, we have some basic steps. So we need to load the data, right? In this case, like it's a computer vision problem. So going to load the image data, going to create a we have a specific way to do in PyTorch. I'm going to show that's efficiently. That's very efficient. And then you're going to need to train the model. Want to train the model, you need to set up the optimizer to define the loss function, and you can set up another other extra stuff as well. And then we train the model, validate the model, and make the inference. So I'm going to start it pretty simple. So the first thing you need to import like torch, these functions, and torch, and from torch and end like neural network has a bunch of functionalities about neural network, and you need to import the optimizer function. So because if you remember the neural network, you need to have a loss function to evaluate the model every epoch, and every time the model interacts with the data, and we compute this loss, this error, and you compute the loss, and you keep doing that several times. You have several different ways to compute this, to optimize based on this loss. So a very common one is this one. I have also the SGT version. I'm going to use PyTorch metrics here to compute some metrics like accuracy, you can compute recall. I have all kind of metrics, including the major one and the main ones at least, included in this package. I need to transform the data somehow because the data is like set of pixels, right? You need to transform it in a way that PyTorch can understand it. This case is using a tensor, the famous tensors. They work like NumPy arrays, but we can use the GPU on it. It's like optimized for these heavily costly operations, computer operations. And we can, from this tutorial, I'm going to use a pre-trained model. So I'm going to use a transfer learning in this case. Yeah. So transfer learning is like when you use a model that was trained in other data, and then we feed our data to this model, uh, passing the image, the targets, what you want to, what's the ground truth of the pictures, what you want to predict, and then the model start like adjusting, updating the weights, so it gets good on our data. From here, just for creating some progress bars, so I can follow up with the progress. This like a print, a better way to print, to log our functions in here, just to the NumPy to show the pictures, so I can take a look. So let's start it here. Okay. This first cell, I think you can ignore it. It works. It's kind of, it raises a warning if you're using some specific GPUs, like from NVIDIA. So it's totally optional. So let's not worry about it. And the second thing is like we need to, like the main thing of PyTorch, different from NumPy, for example, is about the capability of using GPU. Not using only one GPU, you can use multiple GPUs and can leverage the power of a GPU that's way more powerful than CPUs. So if you're going to train in CPUs, it's going to take way more time than working with the GPU. So, and a common way to see if we have a GPU available is like using like this. If you have it, I'm going to use the Couto, that's GPU for NVIDIA. So, and in this case, I have it. If for example, NVIDIA, I can see from my personal computer, I have NVIDIA GeForce RTX 4070. if you go to Colab also provides free GPU instance, like for a limited time, the free version, but it also works, so it can reproduce this code once I push it on Google Colab, for example. And then we have some config parameters. I'm going to place it on the top of the code because in the future, we don't want it in the code directly. You want to have a specific file specifying all the configuration of the model, so it makes easier for everyone. I mean, collaboration, updating the code, so on. So something that we need to do beforehand, for example, set a seed, so you can reproduce it on your side as well, as much as possible, at least. And we need to. I'm going to go to this later, but we're going to use this kind of this hyperparameter. So how many epochs we need to train a model? What's the batch size? I mean, for every, instead of training the computer all weights at once in the epoch, it's a common practice to do it in very small ways. Like every time we go to compute the weights for the data, we just select a small part, a small piece of the data. So in this case, for every run, I'm going to use 128 pictures of my training set. Okay, going to answer this question. So Mauricio has asked a question about UV sync. So UV is like, not sure if you are familiar with poetry or Conda at all. It's the poetry is like more similar to UV. UV is like a new tool to kind of replace poetry. But when you do UV sync, what it's going to do is like to install, it's going to sync the dependencies listed on the Py project TLML. So it's going to do two things actually. It's going to store this, and if you have, for example, let's say I have accidentally, let's say I pip install, let's say scikit-learn as scikit-learn. So let's say I have stored scikit-learn here, and then I need to, if I run sync, because no, it's not a good example because scikit-learn is a dependency here. So let's say site tables. Okay, there's a package called table, for example. I have stored it like in my command line, but it's not specified in the Py project. So when I run UV sync, it's going to make sure it's all stored, and it's also going to remove any extra package because you want to make sure all dependencies listed here. So you see, if I run it UV sync, it's not installing anything because it's all stored already, but it's removing the side table because the side table that I have just installed like manually, it doesn't belong, it's not written in the dependencies. So it's a way to make sure that when you're sharing a project with someone, I think it's a really good tool because not only installs but removes what you have not specified. So let's go. What is the code I was working for? Okay. And here's the parameter for the training. So that's the learning rate. So like the learning rate's like usually it goes from 0.0, some bunch of zeros 1 to 0.1, for example. If you set that too high, it's going to be overfit it. It's not going to find the best, the optimal. It's going to take a. It's going to read. It's not going to reach the best possible outcome of the model if you like too high, but if too low, it's going to take a long time to reach the best, the optimal performance of the model. So that's kind of important hyperparameter to tune and to take a look at. Learning rates, one of the most important, I would say. So in this case, we need to specify the amount of classes because, like I said, we're going to use a pre-trained model. So a pre-trained model, it was trained using a lot of classes, and we're going to leverage the architecture of the model. So have like, it's a deep learning model, so have several layers, have the convolution layers, because like it's a convolution model here, deep learning model. We're going to make it simple. You're just going to change the last layer so it adapts to our data. And our data has only 10 different classes of airplanes, dogs, and so on. And in this case, I'm going to specify it here. I'm going to specify the output of the model when after it's trained, and we want to save the weights, the new weights of the models, right? And that's only for increasing, to make some parallel operations, mainly if you're using CPUs. So that's the configuration. And here, guys, just to make sure we have reproducible results. But even so, you might have not exactly the same results, because the GPU might change. Even if we specify here, the GPU might change. And so we're setting the GPU for NumPy, we're setting GPU for the CPU in PyTorch in case you are using CPU, and also setting it for the GPU to make it reproducible. A better way to do it, well, like to make sure, like to use a deterministic model, but it takes longer to train. Since you're going to run optimizations here, I'm going to train several times, it's not good to do it right now. It doesn't impact that model that much. So I'm going to turn it off. But if you want to make it fully reproducible, I would turn it on, like true. I would change this for true. The model the data going to load here, like these. I need to change I have changed only the older notebooks. So, PyTorch, from Torch, Vision, Torch data sets. Okay. When you have like the data in your folder, like usually with real data, I have the data in your local computer, or like some bucket, someone. So I have the data in some computer, and then that's how it's usually structured. Okay, so like we have the data folder, it have the train folder with the class we want to predict. So we have in this folder called airplane, we have a bunch of pictures that are airplane. Okay, so they are actually airplanes. So have a bunch of pictures that are actually automobile and so on. So have the same thing, has the same structure for the validation set and for the test set. And that's something that's interesting, because here I'm going to use a data set that's commonly used PyTorch tutorials. I think it's small, it's simple, so it's good to use it to avoid extra complexities, to get familiar with all this link between PyTorch, weighting bias, and Optuna. But that's what you would see in kind of a real life project. Okay, and in this case, I don't have like test data as well, and it's highly recommendable, advisable to have test data, mainly when we're using optimization, because the modest only training is going to be is going to see only the training data, the pictures on the training folder. But if you're going to optimize it, and we are going to optimize it, we're going to look at the validation set. And the validation set, since we start changing the model because of the behavior of the validation set, it's not as reliable as it was before, right? Because even though the model hasn't trained on it, it's seeing it somehow, like taking some decisions about it. So it's really good, very important to have a test data that is separate from everyone. That's the last thing we're going to see. Right? So it's like our expectation of a real performance, the real performance in the future data, unknown data. So, and for doing this, you use this image folder with the data loader. Okay, but in our case, we're going to use to load the data sets directly using a function for Torch Vision. Like I said, before like starting to loading the data set, we can apply some transformation in data. So because the data is like picture, and you need to transform it to a way, some way that PyTorch can understand it. And in order to do it, we can specify some set of instructions. So we can specify the instructions using transforms.compose, for example. So we can, for example, make it to tensor that the PyTorch like NumPy arrays, basically, NumPy matrices, and you can normalize the pixels, and you can apply like data augmentation. That's really important. Data augmentation, like changing a little bit the color of the pictures, rotating it, flipping it, adding saturation, these kind of things. It usually helps the model to change a little bit of the training data pictures, so the model faces more variety, right? And it helps it to make more generalizable, to be better at generalization. Not going to use it here, but yeah, we can do it definitely on here. But it don't do data augmentation, the validation transforms and the test transforms. Okay, because usually have a specific set of instructions for the training set, and these instructions, most of it is going to match the instructions for the inference, like in this case, like validation tests and test transformers. But not all. For example, data augmentation is not going to be available on the inference, but the rest of it, yes. For example, normalization, we are expecting to have the same normalization. We also expect to have the same size. We can resize the picture, like to make sure it has always the same size when you're feeding the model, so I can resize it. So in this case, we would use the same resizing option for training, for validation, test, and so on. But the main difference is like this, yeah. In case you want to see, I'm going to show how we can, these values here, I didn't take it out of my mind. I'm going to use a model, and the model was trained using these normalization values. So I'm going to show you how can we find these values for a particular pre-trained model. Okay, I'm not going to use a test set because I don't have it, but just to let you know that, yeah, you can have it. Okay, so now I'm going to download the data. Okay, so for the data set, we can, since we are using this available model in the library in PyTorch, PyTorch Vision library, we can download it directly from here. Okay, and then you can, I'm going to show you how it looks like. So if I download it, it's going to like, it's downloading the file. Okay, in a folder that I just say data. So it just created a folder here called data. It's downloading the files, but it's downloading like a binary version. So it's a bit different of a little bit different of the way I told you before, like for real data. So I have a lot of binary versions here. If you access it, so you can see that's a specific kind of data set, and can actually find something. So I have, let's see how many data we have in the training set. So I have like 50,000 pictures. If you want to access the first picture, you can just access it like here. So that's the first collection of picture plus label. So the first value is like the picture, the values of the picture, like the RGB values, like a huge matrix representing the pixels of the picture, and we have which label it belongs. So it belongs to label 6, but what is label 6? You can find it as well. So there is a mapping here. So class index. So label 6 is frog, for example. So this picture, if you plot it, it probably belongs to a frog. You can also plot it if, for example, if I'm going to turn it out, the transform here, just download it without any transformation, and let's see how it looks like. So let's see the first picture. I have that picture and the label. So let's take the picture of the first. It's very small. You're going to be able to see it, but it's a frog. Okay, it's a brown frog in the earth, something like that. So if you take like another one, it's like a truck, but so for you it's like probably too small. But it's like a truck, and you know, let's see if it's actually a truck here. So it says like automobile. It says like auto. No, I need to print the also print the label. 9. So 9, it's a truck. So that's right. Okay, so that's the data set. You see that if I don't provide any transformation, it's only going to provide the raw pictures. Okay, so and it's ready for this package called peel. Okay, so I have the picture like 32 pixels by 32 pixels. If I provide the transformation, transformer, then it's going to perform this operation here. It's going to convert it to the tensor, to torch tensors, matrices, and it's going to normalize the values using this mean and this standard deviation for every of the 3 channels like RGB. Okay. So that's the data set. And another thing that we have is data loader. So what is data loader? Why do you need it when you already have the data set? The main difference here is because the data loader optimizes the process in PyTorch. So Torch is all about optimization. So if you see it, you're going to, if you study it, you're going to see that I have a lot of similarities with NumPy and other package, but I have the main goal here, the main difference, like they optimize. I think we can have it on GPU. We can have like batches, efficient ways to analyze a collection of data together and so on. So in this case, we're going to use this data set that has a collection of pictures and labels. You are going to split these pictures by some groups. So the group here is going to be the batch size. So batch size we have provided, I think it's 100, 2018 probably, yeah. So we're going to group these in collection of 128 pictures and labels. In the training data, it's a good practice to shuffle the data. So in case like it's all, let's say we have a car, truck. It's good to have like it shuffled to avoid the same class and the same batches with the same, only one single class. And here going to use some workers. In this case, I'm going to use 4, if I'm not wrong. And here's just to optimize a little bit the process for us. And again, we have different, we might have different loaders for the validation and also for the test set. Okay, again, what is the difference? Yeah, perhaps in the test set we don't need that much pet. It's already trained, so it's going to impact it might impact a little bit the performance of the training, but the validation, it doesn't matter. It's all about like speeding up the process. Let's load it and let's see how it looks like. So it is as expected, is a particular class of PyTorch, and it's like a data loader class. So in this case, we cannot index it like this, but we can like make it iterable and interact like over this iterable object. So what you have here, you have two items, just like the data set, but it's a little bit different. Why is that? Because let me see the shape of this. So the shape, let me show the shape of the data set as well. The data set, like take the first one, and let's take the picture. Let's the first collection of eating label. that's the picture itself, and let's see the shape. So you're going to see the key difference here is the order of the values. So I have the channel. In this case, the same is already transformed. This NumPy is a little bit different. Okay, NumPy usually the channel is like the last thing, but we have the channel, the RGB channel, the width and the height of the picture, and in this option here in this output we have one extra value dimension. That's about the pad size. So you're going to that's how we process a bunch of files all together. Okay, with this structure here, that's why we have this 128. And if we go to the labels, you're going to have 128 as well. You see the length of it, 128 labels. So that's about the bet. So it's a different way to optimize it for further computation. Now let's go to the model. So we have like loaded the data. It might differ for your scenario. Like data load is pretty usual in this code here. And then we can like create the model. We can create it from scratch. It's not that complicated, at least for simple models. But you can also use pre-trained models. So for example, I have loaded this model from PyTorch models, PyTorch vision models at the beginning of this notebook. And I can use the pre-trained weights for it, because if I only load the model, I'm going to load the model architecture. Okay, this model has X layers, every layer has these specific features and so on. So you're loading the model architecture, and you're also using the less weights of available for this model. So back then, it was pretty used to use something like this, but trained equal to true. But it's been a while that PyTorch is like changed a little bit the syntax for loading it. And I think it makes sense because now I can specify exactly the weights, because, okay, it's per-trained, but what is exactly the weight you want to use here? So I have like a default value. I'm not sure if default is like the last one, but you can like specify the exact weights you want to have here. So if you see this here, let me see the weights have loaded in the beginning of the notebook as well. So that's the weights from the RESTnet 18. I want to have this particular weight here, and I can also have the transforms for it. So that's the original transform. I could use these exact transforms in my transform operation that I have set it before. Because that's how the model was trained. The original model with these particular weights, they were trained using these transforms here. We can try to leverage it to see if it work, but since like it's the size of 256 in our pictures like 32, an option is like just ignore it, that I'm going to do right now for didactic purpose, or you can like resize it to perhaps 64, and you can change the layer that takes this sizing. That's okay. There are different ways to work with it, but so far let's use a simple transform operation that we have set it. But one layer that we need to change for sure is the last layer that make the prediction. So they have like the reference to the target. The target now is different, right? The target is not the same this model here was trained on. We want to adapt this model to our data. And then our data has 10 classes. So let's change the last layer of the model. Depending on the architecture, the model you're choosing, these last layer might have different names. Okay, so this name is usual for all RESTnet models. but I think it's different for VGG. You have different model architectures. Then you need to see it like one by one of the model architecture you're using for. After that, I'm going to place the model to device to make sure it's the device will have set it again in the beginning of the notebook. In my case, like Couto to use GPU, and I'm going to use it here. Another thing that we're going to do is to compile the model. It's optional. So let me see here, optional. It might like throw some errors. If you're facing some errors while you're trying to reproduce this code, you can just comment out this line, can remove this line, but it's supposed to make the model run way faster. Okay, so it's changed that became introduced in PyTorch 2.0. Okay, and you can have it here. And then we need to define two extra things before going on. So like what's the criterion? So what's the loss function you're going to apply? How we're going to say the model is, how are we going to evaluate how our model is performing? So for classification tests, a very common metrics like the cross entropy loss. So it's kind of seeing the impurity of the data of the categories as a whole. And you can then define some kind of particular way how you should optimize it. Okay. And so you need to pass the parameters and the learning rates here. And there is actually there is an extra thing that I haven't mentioned here, but we have some schedules for learning rates. So what is a schedule for learning rates? Learning rate, like I said, is one of the most important parameters. When it's like too high, not going to find the best optimal place. When it's too low, it's going to take a while. It can kind of get stuck in something called local minima. So it's a very good strategy is like to start a little bit higher, and with time we decrease the running rate, so the model like gets the minuosity, the small details of the picture, so it decrease the learning rate. So it's going to learn like to have some micro learnings, and then we have, I recommend to see Torch schedulers search for that. But it's pretty simple, okay, to implement it, and it helps. I think it helps a lot, the model. Finally, we're going to use some metrics to compute it, and you're going to use the torch metrics. This kind of getting the entropy loss, and here's the accuracy. We can have recall, precision, FU and score, can have there's a bunch of metrics in torch metrics, and for simplicity, let's stick with these two here. So two metrics, and now we can start the training process. Then here is a little bit, the code is a little bit longer, but yeah, that's a common step. If you see, so far I haven't used any class and function, just want to go directly on it, and then you can implement the new things. So for the training, we need to like perform this operation for every epoch. We need to tell the model how we want to perform. So we have a bunch of PyTorch conventions here. So one of them is like when you're going to train, we need to use this model.train to set the model environment in the training section. So like it computes the gradient descendants and computes the optimization and so on. And for every epoch, we are going to restart the loss and accuracy. It's kind of important. It's kind of important to for every epoch, and I want to see how the epoch performed, not the epoch and before the epochs prior to them. Then we need to interact over the batches, right? I can like for image and labels, I could interact over train loader. It's going to work perfectly fine. Just using this here so I can like follow the train progress of the training set. Okay, So it's going to encapsulate the train loader. It's going to show the progress of the training set. So I have like this restriction, and then I'm asking here to not leave the bar after it's done, just not show it anymore to avoid like pollution in the output. So for every image collection of image, because it's a batch, so it depends how many images you have here. It depends on the batch size, okay, how many labels you have. So let's say in this case, we have 128 pictures and labels for each of these interaction. And for each interaction, I'm going to place these pictures and labels into my GPU to run it faster. I'm going to compute the outputs, kind of the method, the prediction of a model, like scikit-learn.predict. It's kind of, that's how it works with PyTorch. So you're going to just call the model, open parentheses, and you pass our pictures. In this case, they are transformed already because we are getting it from the train loader. That's a good observation. And then you have like the loss of these functions. So what's the loss? The criteria of the loss have how, how well did this particular prediction performed in this batch. So I have the output and you compare with the true labels, and you're going to have the loss, and then we start the optimization process. So it's PyTorch convention. Okay, so we need to set 0 grad to restart the gradient. You need to like perform, because when you do that, the model like form a forward process from the input to the output, and then based on the loss that we just computed, we need to update the weights. That's a backward pass. So we're going to update our weights based on this prediction. So we do it the other way, and then we compute the gradient and optimize it using our optimization, in this case ADAM. And then we can like update the metrics. So you're using here the loss and accuracy, and you can update both of them. Okay, update loss, update with the loss were already computed here. We update accuracy by taking here, showing the predictions and labels. And this only for the bar, the train progress bar. Okay, so it can show the results for us. That's one go. I mean, that's the training step. Usually you have this separate in a function, but for every epoch, you also want to see how it's performing the validation set. Okay, so it's trained. You use this batch for train the model. You computed the error, but what about the data that it didn't see? The model hasn't seen yet. So in this case, you go to validation step. So it's kind of the same process, but without training, without compute the gradient descendant. So you just set the model to the evaluation context, reset in case we have some kind of validation loss and accuracy, reset it to have a new metric for this particular epoch, and then we can run this code on inference mode. Okay, it's kind of a conjuncture. So I have like the model evaluation and the contextualization of inference. Usually you also have another way to do it with like no grad. Another option. Okay. The documentation says inference mode is faster, but if the purpose only getting the metric for the validation, I recommend using inference mode. But in case you need to use this process somehow later, then you might want to use storage.noGrade. Okay, let me see if I have some questions. Okay. And the same code for the bar progress to show this time the validation set. Then you can kind of use it. So can run it, but before run it, I'm going to show after every epoch. I'm going to show what is the epoch and what is the train loss, train accuracy, validation loss, validation accuracy. And let's get it done. Something else. I didn't run the model. Let me run everything up above it. Let's work. So here we are the model is like performing the training process, right? At the beginning of this function. So I have the training bar, I have like the accuracy, it's going updated, then disappearing because I asked to disappear with this leave equal to false. But then this section here is like showing the values. So for the first epoch, the train accuracy was like 69%. For the second epoch, it was like 8%. And it's expected. What we expect? We expect that the train accuracy gets even higher and higher. And ideally, the validation accuracy also gets higher and higher. In the case that the train is getting higher, but the validation like stopped getting higher or like started like decreasing, that's a bad sign. That's sign of overfitting. So we need to adjust probably the amounts, the quantity of epochs, perhaps the learning rate, and so on. Like add like more data augmentation, like add diversity in the data. So the have representative pictures in the training set, and that's the job of the data scientist as well, right? So we need to consider all these possible factors. So let me just run it again so you can see that this accuracy and noise is going to be updated several times, and it's based on the batch, because for every epoch we have like 391 bets because we have like 5,000 pictures, right? Divided by 128. So it's going to be the inter part is going to be some of these. Wait it again. Yeah, exactly. So um, that's why you have that amount. Okay, that's why you have like constant updates, because every batch is going to is changing the weights of the model. And once the model is trained, like every supervised model, you need to save the weights, you need to save the model that so that you can use it later, right? And a way to do it with PyTorch is using the torch save. So I'm going to save, for example, the state dict. So the state dict is like a dictionary with all the weights of the layers, and every layer is attached to a particular weight. Okay, you can also save, for example, the optimizer function used, the amount of epochs, and if you want to use more things here, sorry, you can use it as well. Then we have saved the model in this folder called weight. Okay? Uh, and what about the inference? So far, like it was the training process, the inference process. Let's say we want to load this model. So similar, torch save to save the model, torch load to load the model, and you can like ask to to load only the weights of the model. And but one thing we need to do, we need to have the same. Here's not default. Let's realize this one. It's good to see to have the exactly same. But in this case, you don't use it. You don't need it at all. Actually, it doesn't matter because you're going to change to put it here. So again, we need to load the model, and let's load the model, and we need to load the exact same model architecture. We need to put it in GPU as well. I compile. If you have compiled the training version, it's good to have a compiled version of the inference of the model to do the inference, because the compiled version change a little bit the name of the weights in the dictionary, so I can have it. So we load the model architecture, the same model architecture, and then we load the checkpoint that we have saved in here, and then we can just use it. So let's say, for example, we have, let's say, 10 random pictures of our data set. I'm just using this random seed here. So here I'm getting 10 random index of the validation set. Ideally, it should be the test set, not the validation, but we don't have test set here. But ideally, it would be the test set. And then can list the classes, and here you're going to make the inference and plot this picture. So basically, for every one of these indexes, we can have like load the picture. Okay, so remember how I showed how to index the data set. So I'm using the raw picture, not the raw, it was transformed. So I use the data set for a particular random index, getting the picture, getting the true label, and then I'm squeezing it because we need to have, even with not perform a batch operation, we need to have a batch. We need to have like a batch option that it's going to be 1 here to have the same shape of the prediction. So in here, like we get the prediction, but this prediction is actually showing the probability, right? The log-mass the probability of every class. And I need to see what's the class it's if we want to get the one that is the most probable one, so the predicted one. So you need to get this, use the argmax and catch it. And then have some tricks to do it here, because here I have used the original picture. So the original picture, you need to change the shape, and since you have applied some transformation in it, we also need to redo the transformation. Okay, so one thing you need to do is like to place it to CPU, so like we can use the numpy array of it to plot it. I'll just change the order of the channels, because like I said, it was like channel height and width that is in the tensor, but numpy array to plot it is actually, it expects like height, width, and channel. So we're just changing it, placing the first, that is the channel, to the end here. So the 0 is going to be over here. Then we're redoing the normalization and plotting the results. So let's see how it works. Again, I have trained with like 3 epochs only. We haven't changed a bunch of things, but here you can see the pictures and the predictions and the true labels. So here, like predicted bird, and it's actual bird. It predicted an automobile, it's actual automobile. Here it predicted like a cat, but it's a dog, so that's wrong. And here predicts like a cat as well, and it's a truck. This picture is like interesting. I wouldn't say like each of them, but okay. Um, yeah, so that's how we trained PyTorch model without earning stop, without schedulers, but that's the overall workflow. Like getting the data sets, get the data loaders, setting up the training logic, the inference, the validation step, training step, validation step, and also the optimizers and the detectors and the metrics. So that's a general workflow. In real life applications, you're probably going to have extra work for uh, pre-processing the data and post-processing the data. Okay, but let's go to the next notebook. That's exactly the same, but just an increment of it. So let's see what's the difference. So here I have the I'm now going to be a little bit faster because I have seen it already. So the difference here is that we're going to use weights and biases, and we're going to use this dot env environment here. I'm going to show why. So here's all the same, like load, use, like set up the device we're going to use, my case, GPU. You're going to set up to use the config parameters, just like you have done in the previous notebook, setting up the seed exactly like that. And here's the difference. So we're going to leverage exactly the same code, but now we're going to use weighting and biases. So for that, you need to have an account in the weighting biases. And once we have an account, you can create, you're going to get an API for that. In order to take one way, a simple way to to set it up, you can have this file here called .aim, with a common practice in Python projects, where you can store local variables. And a common practice as well, I'm not going to show you because like every kind of token, API key is not supposed to be in production, it's not supposed to be in GitHub repository. That's why the Git, you see that it's a little bit gray because it is in the git ignore file, but you can upload something like this so that people are aware how to use it. So we need to have a .aim file exactly like this, but then you place your API key here. So weight and bias underscore API underscore P. Okay. So if I do it, it's okay. When I run lot.aim, it's going to search for this file here. .aim is going to load the variables automatically. So just checking if this variable exists in the file, I mean the environment, after I have loaded it, and it's okay. And then now I'm going to set up the project, okay, the on weights and biases. This case I need to, let me display it here. I probably need to show it to you in the web browser. So I'm going to show you like, let's first run it, and then I'm going to show how it works. Okay, so exactly the same code. So I have like load the transformers. Here I forgot to load the torch vision like I have done before, like vision import. Okay. Load the data, we load the model, we load, set up the metrics. And here we have one difference. There's the exact same code for training, but by the end of it, I have two differences actually. I'm going to load, I'm going to store the values for training, for accuracy, for loss, and etc. I can log in this like experiment. It's kind of experiment where I have can track as much as things we want. So I can even figures. I can place figures. I can place files. I can log the model itself. For now, just going to log the metrics of the model. So let's run it. And yeah. So after it's finished, I'm going to share my web browser view so you can see. Can see it. So from the code, this project here just got created. I didn't have it before. So you see it's running right now. I can click on it. And then I'm going to have this first model. It has a random name because I haven't set up a name for it, but you can set up names for it as well, tags and so on. Here, probably it's going to finish. I mean, it finished the training. I just need to finish the model. I mean, the experiment. But here I have like how much it increased, the accuracy increased, the values for epoch, and the values for validation. You can change the values here. I have some system metrics as well about how many GPU memory was used, and I can add panels, modify panels, create reports out of it, create filters, organizing tags, and so on. So that's kind of a powerful way to compare models. But so far, I don't have so many things to compare, right? Because it just create this single model here. So let's go back to the code. Okay, and here it is. So I can actually wait and I'll finish uh, and experiment. So the experiment is over. That's the run summary. Okay, and I can like save the model and make the inference just like before. Here it's exactly the same, so it didn't change anything at all. This time, except that this time for some reason you got right the truck. Uh, Again, we're not using a deterministic model, so it's not fully reproducible. So we might have some small difference here. And there are also is only 3 epochs. So that's when we incorporate weighting biases. And how do we incorporate Optuna? It's actually pretty simple as well. I mean, at least the general overview of it. So let's do it. Again, it's exactly the same code, and I'm going to point out the difference. So let's load the library, set up the device. In this case, I'm not going to set up these particular parameters here because um, we're going to use a space of hyperparameters instead of saying like epoch, 3 epochs, like a learning rates. This particular value here for learning rates, I'm going to ask to search smartly in a range of possible learning rates, in a range of possible batch sizes, and so on. So we're going to load it, setting the seed just like before. I'm going to set the transformer just like before, but here we see the difference, right? So here we have this dictionary here. I have this function. Okay, so this function is going to define, is going to receive a trial. That's a particular object of Optuna, and every time that this trial like appears here, the the framework is going to suggest some particular values based on it. It's going to record it internally, and the next iteration is going to look for other combination, and the next combinations, the next iterations, is not random. It's like it goes to the direction that maximize the accuracy, or in this case, minimize the loss of our model. So for example, the learning rates, I'm suggesting values from 0.001 to 0.001. For batch size, I can like try the 3 different values here, just examples, right? For optimizer, I can like try Adam, can try HG. I could use for schedulers as well that I'm not using here. I could use it for providing early stops or anything. Basically, you can provide different transformers and so on. So you can like suggest a lot of things, and Optune also has some ways of finding the most important hyperparameters after a few trials. That's really good in deep learning because you don't want to test it out because deep learning takes some time to run, and the goal here is like to do it like efficiently, but even though it's efficient, it takes time. So that's why in this particular example, I'm going to use only 3 here because again, it's going to take some time. So let's do it like pretty fast just to see how it works. And then we have the common code that we have it, but it's all inside this trial function, this objective function. So that's my space of hyperparameters. Then I'm going to run weighting biases. I'm going to give a different name. This time I'm going to specify the name for it. And I'm going to reinitialize it in the loop. And again, the same code: load data sets, load the data loaders, set up the model. But this time, for example, we can add, instead of adding only the last layer, I'm going to add an extra layer here. Let's drop out, drop some batches. And I can, for example, for this, the criterion is the same, but for the optimizer, there is two options, right? It's Adam or or S GD. So if it's Adam, from the hyperparameter is Adam, I'm going to use Adam, otherwise I'm going to use SGD. So, and then I come to call it. So just creating the optimizing base, taking these in consideration. You can use the same logic here, again, to create schedulers, logic for early stops, and so on. About the metrics, the same metrics. A difference here is we can like compare to get the best accuracy. That's, I think, kind of important to do it, because we're going to perform several trials, and we would like to report the best accuracy that we get in here. The model here is exactly the same for the bar progress and everything. I'm going to log the metrics on weighting biases, and only for the best metric, for the best accuracy, I'm just going to report the best accuracy. So I'm going to update it based on the best possible accuracy, and that's how I should finish this experiment. So I'm going to finish the run. Okay, the run is like, I have set it to run the weighting bias. That's a little bit different as well, right? This time I have set a name for it. Okay, and then finish it. So let's try it. So that's a function. I need to, again, to load the API key, and then I can use from Optuna, I can create an student that's focused on maximize, because in this case, I'm using accuracy as the metric that I want to choose, because we can use any metric possible. I could use the loss function, for example, but in this case, if I had used the loss function, I would need to minimize instead of maximizing it. And then I'm going to set only 5 trials, because we have limited time here, and that's how it works basically. And let's start it. So we create a function specifying the space for hyperparameters, our logic of the model, how the model in transformers should be done, and we need a metric that we need to optimize. So in the metric, in this case, I chose accuracy. It could be like loss as well, and it's going to run it for every one of the values. You can also do these like trial epochs number and test it number. Yeah. Okay, while it's running, let me show the web browser again. If you have some questions, please feel free to ask. In the meantime,
That was, oh, okay, you're moving on. Good.
okay, that's awesome. I think you can ask in the chat, then I'm going to provide some time to provide questions. But if you see here, just to kind of analyze it, so yeah, we have seen how to like create a base PyTorch workflow, how to link it with weighting biases, and how to link Optuna with weighting biases using this base PyTorch workflow. And here, for example, you can see that you see this bell, this green bell here. It shows that it's an active run. So we had one trial, another other trial as well, and you can like just compare it with one another. Of course, it's good to have more epochs. Okay, instead of having like this, it's good to have more epochs. But you can see, for example, that this particular model here, it worked better actually. And that's the one that we started first. Probably the model didn't have time to find good hyperparameters yet. So that should be it. And share this once again. Okay. Now it's still running, so it's going to find possibly it's going to find better hyperparameters, but you need to take some time. So let me. I'm going to stop it. It takes some time. Let me see. This is finishing. Let's finish this one finish, and then we can stop it. Okay, let's stop it. But you see, it's not taking that long. Of course, it's only 3 epochs, but it's not taking that long. And you can see, this here is not going to work because I stopped this, but you can say, for example, for the study, once it's finalized, we can get the, and this here wouldn't work. I need to go back. We can have get the trial, so we can have the best trial, and we're going to show what are the hyperparameters, and then you can use these hyperparameters in our own model, right? And that's how it had finishes here. So now I have to know how to use the base PyTorch workflow, link it with weight and bias, use Optuna to create to make best optimizations. I don't think I'm going to have time to go over the code, but I promise that in the next like 20 minutes, I'm going to push all the code to the GitHub repository, so you can take a look at it, try it for yourself. I'm going to provide instructions to run it. With UV, it's pretty easy, pretty simple to reproduce the whole environment. But the main goal is like taking this code, the code that we have worked so far in notebooks. If you want to like follow best practices to make the project sustainable, to make it easier for our future ourselves, and for people that we are collaborating with, it's good to have it source a folder with modularized code. So we're going to take every piece of logic. For example, have like training step. So for the training step, we can create kind of a training function to a training class to do it. Where the training class is going to receive a lot of the a lot of the configurations that you have provided, and all the logic of the training epoch is providing a function. All the logic for the inference model is also provide the validation set is also provide in a function. Then we have the function to train it all, because we have a training step with the validation, and then in the training function, the main one, you're going to to perform the training step and the validation step several times, the amount of epoch times, and that's way better by wizard to do it like this. Same thing for data sets. So instead of repeating to have a lot of boilerplate code, it's way easier, way better to have it like on our own functions. It's exactly the same code, I just restructured it in a better way. So like create transformers, get data loaders, and so on. And finally, something that I really like to do is like you can provide a load configuration file. It can be on a structure like this. I particularly like this structure. I have a folder outside of the source model, because this here is like the code, the main code section. So I have something out of it called configs, and then I have like the default version. You can have different specifications from here. So I have if you want to what are the steps that we're going to do in transform data, validation data, what are we going to pass in Optuna. So that's the specifications. And then from our code, from our source code, you can load it. And you can like manage any kind of specific complexity or customization that we need to do after receiving this configuration file. So we can load it and use it in our model. So if you see here, for example, is expecting, not this one, but can create models for every one of these expected values. You're going to pass, going to load the config function and use it from it. So good practice to have like scripts like train and yeah, so like you load the configuration and then you use the configuration node to do everything basically. It's way more transportable for other people to see what's going on. Let me see the questions right now. I think we can have. That's a good question. So question, CFAR image like 32 to 32, yeah, but the model expects different resolution. Yeah, the model expects like higher resolution. So it's not actually matched, right? We need to try it out to see how providing different resizings of the picture would work, because we can like increase our pictures to have a bigger size, like a higher resolution based, I mean, higher size, right? Not exactly higher resolution, but to match the expected size of the image, we can like, usually it's actually the other way around. Like when it's kind of create chips of the image, we cut a big large image in several smaller piece of pictures. But in this case, it was working good. I didn't show the whole picture, but if you run it like with 10 epochs, 20, 30 epochs, it's going to work good regardless. Okay, and if we resize it, it's going to take longer as well. But you can try it. You can try to change. You can try changing the resize options, and you can also try changing the layers that expect by default this 200 and something resolution. Yeah, I will upload this code, but I need to add remote option. Meanwhile, do you have any extra questions? I think the time is almost over, but we have so how the hoods are matched. Yeah, it works regardless. It works regardless. So because it depends of the architecture of the model, but even because I have these convolution layers that is we expect as we're expecting a specific input size, but this convolution change reduces the picture for a particular size. But yeah, that's not fully sure actually how it's working behind the scene, but it worked. So I tried with different resizing options. Some of the resizing options didn't match, so probably should have like multiples or something like that.
Yeah, that was a great talk. I don't see any more questions. I don't want to cut you off if there are other questions, folks, but
Yeah.
if you
And
figure.
in the meantime, I'm going to
Awesome.
upload it. I just need to vinculate it with my local repository, but like in 5 minutes, it's over the repository, and that's the one that I talked to you. Okay.
Great. So I guess folks are to look for that in a few minutes if there is that what I'm hearing. Yeah.
Yeah.
Perfect. Well, excellent. So that's I'm impressed that you can keep on talking for an hour and a half. I think that's
I think I talked too much.
no, it's just that you could go on that long. So, well, thank you very much.
Thank
I
you
hope,
for.
yes, I hope folks got a lot out of that. It looks like you're getting some good kudos there. So, with that, I'll say thank you, everybody, for coming to the second day, I guess, of PyData Global. We'll be continuing tomorrow on our third day. Hopefully, you can all join us then. We can continue any conversations that folks have or have questions that they want to ask of our speakers. You can do that over in Discord. But with that, I think I'll end the session here with a final thank you. And I hope everyone enjoys the rest of PyData Global. Take care, all.
Yeah, thank you. And it's there already. Okay, the code is in there.
How
But
fast?
okay.
Perfect. Alrighty.
Thank you so much for joining this.
Yes. Thank you all. Bye-bye.
Bye bye.